So that is heat evolved at constant volume. What about when the volume changes, which is a more realistic situation? If a chemical reaction occurs that's open to the atmosphere in, say, a beaker, now the pressure is constant, but the volume can change. Often, we are only interested in the heat that is exchanged and not the work that is being done. So the enthalpy of a system is the sum of the internal energy and the product of its pressure and volume. So H is equal to the internal energy plus PV, just because I'm telling you so. Enthalpy is a state function, doesn't depend on how you get from one place to another. Enthalpy change is delta H. That's the heat evolved at a constant pressure. So here, delta H will be delta E plus P delta V. This isn't delta P because the P is staying the same. So here, delta E was Q plus W, and we put a P on there to indicate that this is Q at constant pressure, not at constant volume. So W is negative P delta V. So negative W is positive P delta V. So here, this P delta V is negative W, and poof, the W's go away. And this is how people mess with equations and find, and also defining terms in a way that makes things actually work. So at constant pressure, the enthalpy change is equal to the heat. Delta H is equal to the heat at constant pressure. Delta H and delta E are often similar in value. They are very similar in concept, right? Delta H was delta E plus pressure times the change in volume. So delta E measures all the energy exchanged, both heat and work, and delta H is only looking at the heat exchanged under constant pressure. Where does this difference matter? It matters for reactions that either produce large amounts of gas or consume large amounts of gas, and so have really big volume changes. So if we stay away from those, we can basically use these numbers interchangeably. They're very, very similar, which is good because they're easy to get confused. So lighters are usually fueled by butane. When 1 mole of butane burns at constant pressure, it produces 2658 kilojoules of heat and does 3 kilojoules of work. What are the values of delta H and delta E for the combustion of 1 mole of butane? I would not ask you on this in exam. Ask X. This would not be a good exam problem. So we're producing heat. So Q is negative 2658 kilojoules. And it's doing work. Is that negative or positive? That's negative. So we learned that there was one thing that was Q plus W. What was that? Delta E. And delta H is just Q. So here is Q. Q is negative 2658. So these are saying, well, delta H is either negative or positive. Well, it's not positive, so we can cross out this guy. And without actually doing the math here, is delta E negative 3 kilojoules? No, because that's just the work. So now we have to choose between these two delta E's. We're going to add these two numbers together. Are we going to get negative 2655 or negative 2661? Negative 2661. So this is the answer. Now, those values are very close to each other, right? So in Chem 1A, we just really don't worry about the work part at all. The signs for delta H and delta E follow the same conventions. So if delta H is positive, energy, heat is being absorbed by the system. We call this an endothermic reaction. So thermo refers to heat. So this is heat into the system, right? Endo, like into. When delta H is negative, heat's being released. Exothermic, heat exit. So exo is going out, endo is coming in. Again, think about money in your bank account or your Venmo account or wherever you keep your money. We've talked about chemical hand warmers that have iron in them, and the iron reacts with oxygen. And this is an exothermic reaction. It releases heat into the surroundings, and then it warms up your hands, because your hands are part of the surroundings, right? So that's an exothermic reaction. Another example is the burning of natural gas. Combustion of anything is going to be an exothermic reaction. Because what do we know about fire? It's hot and you shouldn't touch it, right? Most of us learned that when we were like 2 or something. Hopefully it didn't involve blisters. An endothermic process is the opposite. It absorbs heat. So you can buy instant cold packs, right? Sometimes they come in a first aid kit. And you break some seal inside and you squish it around and it gets cold. But you didn't refrigerate it. There's no ice in there. It just got cold. How does that work? That's an exothermic reaction. As the reaction occurs, it's pulling heat in from the surroundings. If the surroundings is losing heat, what's happening to its temperature? It's going down. Any questions? That's the one that just doesn't seem possible somehow. This one makes sense. And I'm not sure why the difference, but this one is like, well, how can something just get cold? And yet we're okay with something getting hot. We're okay with stuff burning, maybe because that's something we run into all the time. But we don't see many endothermic reactions just in everyday life. Okay, so we do need to be able to identify processes as exothermic or endothermic. And we always have to think of, well, what is the system and what's the surroundings? So it says identify each process as exothermic or endothermic and indicate the sign of delta H. So an ice cube melting. Is energy going into the ice cube or coming out? You can think of, well, how could you make it melt faster? Put it in a pot on the stove and heat it up, right? By putting more heat into it, you'd make it melt faster. So that's endothermic. And the sign of delta H would be positive or negative? Positive, energy's going in. So delta H is larger than 0. Okay, nail polish remover quickly evaporating after it's accidentally spilled on the skin. So you've got the nail polish remover that you spilled on your skin. Oh, here we have some nail polish remover. Ooh, that's cold, right? So it's evaporating, right? My skin is not part of the system. My skin is part of the surroundings. What does my skin feel? Cold. It feels cold because heat is leaving my hand, right, and going into the nail polish remover. Again, how could you make something evaporate more quickly? Heat it up. Okay? So this is also endothermic. Delta H is going to be positive. The heat energy is going from my hand into the nail polish remover. Gasoline burning within the cylinder of an automobile engine. Exothermic. Pretty much any time they say burning, exothermic. Because what happens to the engine as it burns gasoline? The temperature. It gets hot. It can get really, really hot. So heat is leaving, so delta H is negative. Any questions? The previous example with the Q and the W, the delta H, that was not a good exam question. This would be a good exam question. Identifying endothermic and exothermic. So exothermic reactions give off thermal energy. Where does the energy come from? So the internal energy of anything is equal to its kinetic energy plus its potential energy. So when something burns, the kinetic energy can't be the source, because if it was, the temperature of the object would get colder, right, as it lost kinetic energy. So that's not the case. It's the potential energy. So in a chemical reaction, the atoms get rearranged, and their potential energy is converted into thermal energy. So this is like the piece of, the big metal weight on the roof of the building, right? Being pushed off the edge, and that potential energy gets converted into another kind of energy. Here the potential energy is being converted into thermal energy. So what's happening here is that weak bonds, oh, there's a typo. Weak bonds are broken. It takes energy to break bonds. And these atoms are holding on to each other, and you have to break them. A weak bond is very easy to break. It doesn't take much energy. A strong bond takes a lot of energy to break. So if you put in a lot of energy when you break the bond, what happens when you make the bond? It releases energy. Because you can't go forward and backward and have a net increase or decrease in energy. Right? Because the energy of the universe is constant. So strong bonds get formed, and they release a larger amount of energy. So in an exothermic reaction, we've got weak bonds being broken and strong bonds being formed. Energy gets released. The opposite happens in an endothermic reaction. Strong bonds get broken and weak bonds get formed. And so it absorbs energy. An endothermic reaction happens in a flask. What happens to the temperature of the flask? So the reaction is endothermic, meaning heat's going in or out. In. Is the flask part of the system or part of the surroundings? It's going to be the surroundings. So this says that heat is going into the reaction, so will the flask get warmer or colder? Or cold? Well, heat is going into the reaction. Heat is leaving the flask. If we take heat out of something, does it get hotter or colder? It gets colder. So these can be hard to think about, okay? Because most of the time we're monitoring the heat exchange with the surroundings and we can't really tell what's going on in the reaction. But like my skin can detect that it is losing energy, right? So energy must be going into the reaction or the process. Stoichiometry again. Now we can look at energy being involved in stoichiometry. So the enthalpy for a reaction, enthalpy change for a reaction, is delta H Rxn. It's also called enthalpy of reaction or heat of reaction. And when you call it heat of reaction, then delta H Rxn makes a little more sense, right? H for heat. This is an extensive property, meaning it depends on how much stuff there is. If I burn 2 drops of gasoline or 2 gallons of gasoline, does that affect how much energy is released? Of course it does. It depends on how much reactants we have. So just because everybody agreed, we calculate the heat of reaction for the number of moles of reactants that are in the reaction as written. So this is why we took Q and divided it by the moles in that previous example with the hexane. So here we're talking about propane burning to form carbon dioxide and water. And over here it says delta H is negative 2044 kilojoules. What this means is that 2044 kilojoules are given off for every 1 mole of propane that burns. This much is given off for every 5 moles of oxygen that burns, for every 3 moles of CO2 that's produced, and 4 moles of water that's produced. So there we have a way to convert between moles of something and energy. Consider the following thermochemical equation. 2 A's go to AA. That sounds like a joke. Delta H is negative 51.0 joules. What is the heat associated with the reaction of 6 moles of A? This is the amount of energy when we burn or react 2 moles of A. So if I do 6 moles, how much bigger is it going to be? How do you make 2 into 6? Multiply by 3. So it's got to be one of these 153 answers then, right? Because to get from 2 moles to 6 moles, I've tripled the amount of stuff reacting, so it makes sense that I'm going to triple the amount of energy, amount of heat. Is that going to be positive or negative? It's going to be negative, because this is negative. Any questions? Is it just me, or have there been a lot of 5.5s in this lecture? 55.0 gram. I mean, it's just showing up. I'll have to go back and look at that. That's weird. Ammonia reacts with oxygen according to the equation 4NH3. Well, you can read that. Calculate the heat in kilojoules associated with the complete reaction of 155 grams of ammonia. So I've got 155 grams of ammonia, and they want the heat in kilojoules. So here we've got a chemical reaction happening. Stoichiometry is almost always going to be involved in. So I like to use that balanced chemical equation to organize things. So I have 155 grams of ammonia that is reacting, and they want to know the heat. Well, the reactants and products aren't related to the heat, but delta H is, right? This is negative 906 kilojoules for every 4 moles of that. So, again, we can always start stoichiometry problems with grams to moles to grams. Are we starting with grams? Yes, we are. So we're going to go from grams to moles, and then I want to go to kilojoules. Do I have to go to another mole first? No, I don't, because this I can relate to any of them, whichever one I need. So I can just stop here at kilojoules. (155 grams of NH3. I'm going to convert that to moles of NH3. And then I'm going to convert that to kilojoules, and I'm going to divide by moles of NH3. I need the molar mass of ammonia. I'll just save some time at 17.034. And then here's our new thing, kilojoules per mole. So here's the kilojoules, so negative 906 kilojoules for how many moles? 4, because of the coefficient here. So 155 divided by 17.034 times negative 906 equals negative 8244.1 kilojoules. Did I do my math right? Oh, see, I do this all the time. You know what I did? And I was going to warn you about this. I forgot to divide by 4. Because so many times there's a 1 on the other side. So, forgot to divide by 4. Let's divide by 4. Somehow I knew there was something wrong with that. Negative 8244.1 divided by 4. Scratch that off. 2061.0. How many sig figs should I have? 3. I've got 3 in my mass. I've got 3 in my delta H. So we could call that negative 2060 kilojoules, which could be dangerous. We call it negative 2.06 times 10 to the 3 kilojoules would be a better answer. Questions? Okay, one more question. What mass of butane in grams is necessary to produce 1.5 times 10 to the third kilojoules of heat? What mass of CO2 is produced? So here we have an amount of heat, and we've got 2 questions. We want the mass of butane in grams, and we want the mass of CO2. So if I'm talking about grams to moles to grams, and let's talk about the first question first. Am I going to end up with grams? Yeah, what mass of butane in grams? So I want to end up with grams. So this is grams of butane, that's moles of butane. But what am I starting with? I'm starting with kilojoules, right? So kilojoules goes directly to moles, so I don't need to do that. Starting with kilojoules, going to moles. Okay, 1.5 times 10 to the 3 kilojoules. And then I'm going to go to moles. Divide by kilojoules. And then I'm going to go to grams divided by moles. And this should specify moles of butane. My relationship between kilojoules and moles comes here. It's this many kilojoules per whatever the coefficient is, number of moles. What is weird about this chemical equation? It has a fraction in it. But we're going to use this for the reaction as written, even if it seems weird. So we've got 1 mole of butane and negative 2658 kilojoules. And then we're going to need the molar mass of butane. Just going to do that real quick. 58.12. 1.5 EE3 divided by negative 2658 times 58.12, negative 32.799 grams. What's wrong with that? Can you have negative mass? No. Negative mass is ridiculous. What happened here? Well, here we're producing this much heat. So would that be negative or positive from the standpoint of the reaction, the system? It would be negative. So our starting number should have been negative, and we do end up with a positive. And 2 sig figs. Oh wait, what did I do? I wrote with the eraser. So 33 grams of butane. So that's kind of a practical question, right? I need to give off this much heat. How much butane do I need to burn? Then it also asks what mass of CO2 is produced. Well, I mean, we could do grams to moles to grams starting here, or we could just do kilojoules to moles of oxygen, to moles of CO2 to grams of CO2. So the moles of CO2 in the kilojoules. It's this many kilojoules for how many moles of CO2? 4. to remember to include the 4 in the math. And then the molar mass of carbon dioxide is 44.01. So 99 grams of CO2. Any questions?